Sure. So my presentation is primarily on design of the processes in advanced manufacturing. The primary interest here is in digital twins and machine learning to train the systems to do processes like advanced manufacturing of complex materials. The motivation for this was, we've been in this business for quite some time, was a process that was given to us by a combination of Gildemeister and Morisecki. They wanted us to develop digital twins of these additive manufacturing machines. It was a prototype in 2015. They primarily take STL files. These machines then deposit powdered titanium, iron, variety of different materials. The material is entrained in an argon jet. It's powdered. You can see there's a lot of material waste, huge residual stresses. It's operating roughly at about 5 times the actual speed. This is important, this section here, which is essentially it's spot welding the material on contact. The machine is moving the part on a 5-axis spindle. The laser, for safety reasons, is always vertically downward. So this machine, it will go through a complicated series of events. It will move the part around. It has a variety of different abilities in terms of the dexterity. As I said, it's a 5-axis spindle. It will build a variety of different features, but there are some serious problems. Number one, the amount of material waste. You can see the huge residual stresses. So as a solution or partial solution, this machine also does the subtractive part, because additive manufacturing by itself is hopeless. I mean, we really know that in reality. It also has to have subtractive capabilities as well for machine tolerances. So this gadget takes a subtractive milling device and then starts to clean up the mess that the additive manufacturing made. And of course, then it goes through a complicated series of adding, subtracting. And you can imagine this machine is not the easiest to manipulate. In fact, at the time in 2015, it was entirely open loop, which simply meant that if the machine screwed up, it just went wild and it kept going. Considering that the parts are rather expensive, as you can imagine, titanium, they're not small, that the types of things that they could create, one wanted to have some kind of a digital twin to control this process. So this was the motivator for a variety of different projects that we had with a number of companies in the Bay Area. Some of them you see at the bottom. Apple was one of the main pushers of this. They're quite heavily involved in additive manufacturing for obvious reasons. Autodesk, BASF, Boeing, etc. So the motivation for this is to create replicas of the workings of these machines. In this case, this is a liquid titanium powder, but it's ionized, so it has the ability to actually have some coherence. We then modeled the interaction with Maxwell's equations or highly directed ion beams, electromagnetic fields, to basically process the materials. And in this little simulation, what we see is it's the temperature profile of the laser being rastered back and forth. So that's the motivation for a variety of these things. So the idea is, of course, with all digital twins, we have some kind of a model that we hope has high fidelity. We want this model to match some desired response. Either it's experimental, synthetic data, or entirely as an optimization problem. We develop the digital replica. We check the difference between what we have and what we got. We take the error and the appropriate norm. We then extract the optimal settings by allowing the machine learning algorithm to constantly retrain the method until it gets down to as good of a parameter setting that it can. Now, there are a number of different applications. As we all know, we're all working in computational mechanics for a number of years. Either the development of very fancy robots, which are interacting with this deposition process. So we're interested in overall optimization of these types of systems. The optimization in the more detailed case of the deposition of the materials at the smallest scale. In this case, it's a functionalized material where we have a green binder. It's usually a thermoplastic, and then metallic or electromagnetic flakes to give it some kind of electrical functionality. Of course, in the Bay Area, we're mainly interested in electromagnetic and electrical types of responses for obvious reasons. They build a lot of gadgets. Also, the interaction of lasers and the target materials. So we do a lot of fast Maxwell type solvers where we're interested in the detailed interaction of the lasers and the targets. In this case, we're looking at the heat dump. And then, of course, I think as Stefan said in the previous talk, we do a lot of voxel calculations for extremely fast stress analysis of what has been deposited. Over the years, we've extended these kinds of thoughts to many different other applications which are outside of the manufacturing realm, but you can imagine one in particular is I guess, aerial firefighting, which you can imagine due to California burning up. We're now interested in taking those kinds of methods to train other kinds of more complex systems. Essentially, in detail, it boils down to this. We compute the DNA of a system. We replicate it or represent it as a genetic string. Then we optimize the genetics of the essential DNA of the system using a combinatorial optimization scheme. And it's very similar to classic genetic algorithms, but with much more industrial grade optimization. I'll talk about that momentarily. So our basic motivation is driven by digital twins. Our main manufacturing driver these days is for manufacturing of food systems. That's obviously a very big deal. It's most of us in computational mechanics never look at those areas, in particular with the Mars Corporation. You can imagine designing candy bars. That's an entire additive manufacturing process. Cereals, foods, things of this sort. People are constantly extruding and depositing materials. So the food manufacturing business was also a huge early adopter in these kinds of processes. And again, those kinds of systems basically look like this. We're essentially designing with additive manufacturing partners the actual design of the food themselves. So how you deposit a waffle, how you deposit food, things of that sort. These are also additive manufacturing processes that are somewhat complicated. So anyway, let's get down to the details. So we're going to talk a little bit about the manufacturing, 3D robots, the optimization, and how this works. Our primary interest, as we said a little bit earlier, was in the additive manufacturing of large-scale machine parts. It was primarily driven by energy analyses, so essentially designing thermoelectric cables, generator components, turbines, things of that sort, and using additive manufacturing and advanced manufacturing in general to design very specialized parts. So the specialized parts, of course, in this case, could be a composite thermomechanical component, such as a turbine blade. There are many that are now being fielded that go beyond simply titanium super nickel alloys, but they now have some combination of ceramic and metallics. So again, the basic idea is we have a computer model, we have some type of desired response, we run the computer model, it doesn't match the response, we take the error and we keep adjusting the parameters. So the idea then is that we represent these parameters as a genetic string, and then we attempt to minimize the appropriate norm between what we simulate and what we have desired. And we'll show a little bit more details of that momentarily. So the basic approach is that we take a large number of these parameter settings for a typical model. We run them all randomly. So we have basically several different random states. We run the responses. We rank the responses based upon how well they did compared to our desired response. So we compute the genetic performance of one of these ranked parameter settings. We then breed the strong genes, meaning we retain the ones that have done well, meaning they're very close to what we desire. We throw away the weak genes, and we repeat this process over and over again in a tournament of champions. Very similar to genetic algorithms, but some twists in terms of the machine learning aspects that make this thing somewhat faster than in previous incarnations of these kinds of non-convex, non-derivative optimization techniques. Easily parallelizable, easy to implement, insensitive to the number of parameters. This has always made it a relatively attractive approach for these multi-stage, multi-component processes. One thing in particular, once we get down to a typical optimal state that we feel is homing in on the correct set of parameters, we usually then switch to the classical gradient-based methods if the cost function is relatively smooth. Oftentimes in these kinds of problems, it's hopeless. The multi-stage, multi-component aspects of this make this thing simply impossible to have any kind of smoothness or convexity, even at the smallest scales. So let's look at a typical example that we deal with. One in the Bay Area, of course, is solar panel design. The main idea here is that we usually have a multi-stage, multi-component process where we have an easy to form binder and we functionalize the materials with randomly distributed dopants. So the dopants could be to endow some type of elastic, thermal, electrical, magnetic, or optical property. The problem is we have the usual tyranny of scales. We have at the microscale some mixture of materials. At the mesoscale, we have some type of pattern that we want to put onto the surface. In this case, it might be a complex microelectronic component where we have several different things that we have to blend together to make the appropriate leads. And then we have the macro scale where we have the robot. Now, just as an example, if we were going to create the Olympic rings and we wanted the robot to do something of that sort, the robot in this case, as I'm exaggerating just to allow it to be able to be easily visualizable, it's squirting out a bunch of material. And if I had specified the pattern and the type of material here, I would have to do the inverse kinematics and the inverse material optimization to figure out what types of materials should I combine on the fly? How should I control the kinematics of the robots? So the typical problem is that we have usually 4 material groups. We either have a nanopowder, which is extremely difficult to manipulate because of the electromagnetism at the smallest scale, which makes these materials stick together. Also, they're toxic. And of course, as I think maybe Paul knows, you can ingest these into your lungs relatively easily. So this becomes an expensive proposition if we start to use these small scale powders. We have easy to form binders. In this case, for the solar panel kinds of cases, this would be something like silicon or a material of that sort. And we then have metallic flakes and then potentially some types of electromagnetic materials. So we usually try to combine these 4 materials on the fly within a robotic setting. So let's look at a typical example. We specify the types of materials we want on the surface. We have a certain pattern shown here in the dashed line that we want to specify, and we have the following machine learning parameters. We have the kinematics of one component of the arm, the kinematics of the second component of the robot arm, the kinematics of the third component, and then of course, the interaction of the extruder where a lot of the interesting physics are. For example, the pressure that we need to apply to push this complex material through the extruder, electromagnetic fields. Often what we use is something called electrohydrodynamic printing, where we basically push the material out, we ionize it, and then we draw the material to the target using an electromagnetic field. So there's a number of different processes that are going on at the same time. In the example I'll show is simply what we call no vacuum chamber approach. It's basically free form where the materials are being combined on the fly as the robot is attempting to push them onto the surface. So the performance metric here in this case is going to be what the robot did, shown here in solid, and what we want the robot to do, which is the figure 8. We take the L2 norm and the difference between the dashed and the solid. We give the robot a score based upon what the parameter settings were. We say good robot or bad robot. Good robot has a low error. Bad robot has high error. So basically we then reward the good robot by allowing that to breed further in the future, meaning it can produce offspring. The bad robots, we melt them down and put them in the junkyard, and we create new robots to compete against them. So mathematically speaking, in an optimization approach, we run the entire simulation. So basically the simulation runs. If it gets close to the target that we want, meaning the pattern and the right types of materials, it has a good score. If it has not achieved the pattern that we want, it has a bad score, and we keep doing this type of thing recursively. Let's look at the details of a little bit more. Here's a simple example. Of course, more of our industrial strength problems are far more complicated. Essentially, what we do is we track where the extruder is. The extruder is depositing this piece of material here shown on the left. We want it to make this pattern. We have the kinematics of what the piece of material is once it exits. So one of these little pieces of material, we give it by the position vector R1, R2, R3. We know where it is. We take the time derivative as we teach kids in Technische Mechanik 3. They basically compute the velocity. They then compute the extruder velocity, which is an extra added velocity of pushing the material out. And we have now the position of one of these pieces of material as it exits the extruder. We compute then the freeform dynamics of the material, which essentially boils down to F equals ma. We have the velocity of one of these materials. We have its mass. We have the Lorentz force, because this could potentially be ionized or electrified. We have gravity, and then we basically have also drag, because in many cases, there are cooling fans, inert gases, things of that sort to keep the material in place. So if we have extremely strong fans, these materials could be pushed off target. So all of these things have to be taken into account for the dynamics of each piece of material as it exits the system. At the same time, as we know, obviously for additive manufacturing, these materials have to be heated up. So we also have, from the first law of thermodynamics, we have the temperature of each of these blobs of materials, its conduction with its surroundings, its convection, its black body radiation using the classical black body equations. And then we also potentially have hydrodynamic heating, because these materials are being deposited at extremely fast speeds, so they may actually be heated up by the surrounding inert gases as well. At the same time, we have the material properties, so we have to take into account all of this. We use mixture type theories, and of course, that's something we all know about. There are two possible approaches. Use the Hashine-Strickman bounds as an example, since these are randomly distributed isotropic materials. Estimate the elastic bulk modulus, the shear modulus, the thermal conductivity, electrical permittivity, magnetic permeability. We go after all of the different properties. The other approach, which makes, of course, the simulation slower, is to voxelize everything that gets deposited and essentially treat it as three-dimensional voxels. That's still rather fast, actually much faster than classical finite elements, but of course will slow down the processes somewhat. So usually what we do is we run the simulators with the Hashine-Strickman bounds first. Once we home in on optimal types of states, or what we believe are optimal states, we'll usually switch to a voxel analysis to compute what's going on. So here's a typical example. We have a machine learning parameter system, again, for ARM1, ARM2, ARM3, electromagnetic fields. We have the material properties. We want a certain pattern shown here dashed. We have something here that is solid, which is, for as an example, one of the different responses. We discretize the velocity and the position of each piece of material as it exits the system. In this case, I'm showing, just as an example, an explicit forward Euler scheme. I've coded it myself. It's relatively fast. In fact, on the laptop that I'm making the presentation from, this entire simulation takes 1/30th of a second. Not one time step, the entire simulation takes 1/30th of a second. So what that means is, if we go backwards and we ask ourselves, how many simulations can we run? We can run roughly 108,000 possible choices of what this robot could have done. Unfortunately, that's still too slow. With these multi-parameter systems, we need on the order of millions of possible tests to saturate the design space to look for the optimal parameter settings for this entire process. This is where the machine learning comes in. Essentially, what we do is we rank the robots based upon their choices of what we have for the parameter settings. We generate the population, we compute their performance, we emphasize the ones that have strong genetic behavior, meaning they come close to what we want. We eliminate the weak, and we repeat the process over and over again. Again, I've said this multiple times. Essentially, this is a non-convex optimization scheme where we're driving the system towards what we believe to be our global optima. So again, not sensitive to gradients, not sensitive to local fluctuations. And as I said, once we get close to these, what we believe to be global optimal states, we may switch to a gradient-based method if the convex function is smooth enough. Here is an example. We take a problem where we had the figure 8. We run the robot over and over again, asking it to create this figure 8. First possible guess, the robot goes wild, sprays the material everywhere. It's not going to get anywhere close. The curves here on the green and the red indicate We ran the simulation 100 times. We took the average of the population of all the possible robots for the very first time when we guessed. We get roughly about an 80% error on average. However, there was one robot that was only 70% in error. It had slightly better characteristics than all the rest. We reward that robot and emphasize its behavior, and we do this over and over again, tracking what the population of all the robots are doing and what the best possible robot is doing. So within 1 to 2 iterations, again, with these generation of generating new robots, killing bad robots, new robots, killing bad robots, and so forth, we're able to get the solution error down from 80% down to 4% in roughly about 20 minutes of laptop computation. So the idea is that we train the robot system to be able to deliver the best possible responses we can get. Of course, the best in this case were a number of parameter settings. For example, the theta 1 represents kinematics of the first arm, kinematics of the second arm, extrusion velocity, electromagnetic fields, and so forth. One thing to draw your attention to is that the error that the systems finally deliver as they're in their optimal states are all roughly the same within almost 4 decimal places of error. What that allows the engineer to do is to pick several different parameter settings. As you can see, there are many different parameter settings that achieve more or less the same optimal state, which then cost comes into consideration, meaning that depending upon which of these different parameter settings is the least expensive, the engineer then can pick those. So that's the overall picture. All the rest now starts to become details. How do we do the careful analysis, for example, of the electromagnetism? So in this case, if we do a full CFD analysis of what's coming out of the robot with the multi-physics of all of the different materials and electrified here, this type of simulation takes usually 1 to 2 minutes on the laptop. That's still too slow for optimal consideration. If we're thinking about doing several 100,000 design runs, this would only be achieved in parallel. It would be very difficult to be able to do this on the fly for every single iteration of when the robot is moving. So this is something, or an active area of research right now, is how we do model reduction to figure out exactly how we can still get better physics into these models and at the same time capture the intricate complex behavior that we see, for example, when a piece of material is being deposited. Unfortunately, this drags in Maxwell's equations. There's no way to avoid it. We have the electromagnetic fields of the target, but that's basically where we stand at that case. This is mimicking several of the different classical printing processes that were pioneered by Xerox. I don't have time to go through this, but I'll essentially say that right now where we are is essentially on the detailed fluid mechanics of these complex materials, multi-phase, how they behave, how they interact with one another, their instabilities. In this case, it's a Rayleigh plateau instability of exactly how these materials break up into droplets. Just to give you kind of a zoom on exactly the details that we have to deal with, it's a large number of contact mechanics, interactions with the substrates. In this case, we're using a combined discrete element method technique and CFD combined together. As you'll see, the materials break up in this case and then reconnect. Of course, this is far too slow for optimization purposes. So oftentimes what we do right now, our default is to run it with the simple models and then to home in when we get close to an optimal state and start to take out the big guns and do these kinds of processes in detail. I won't go through many more of the details. I've uploaded a lot of this on the website just to give you an idea. Essentially, we have many more processes where we have to deal with the lasers, the interaction of exactly how the electromagnetic fields and the high asymptotic states deal with the targets, how they heat up the materials, things of that sort. Again, more complex, but again, quite doable, but not for fast optimization type schemes. As Stefan said a little bit earlier, we do a large number of digital image type problems with voxel calculations, again, going back to then continuum analyses. We don't have to beat that tired story. We know exactly what we're doing there. The classical thermoelastic and thermoplastic type behavior. we treat everything as voxels. We do very vast voxel calculations. And then in this case, after going through this process, we can compute things like the von Mises stress, how the evolution of the stress is over time, whether the material will crack, where's the propensity of cracking, and then again, embed that into the optimization of the robotic overall system. So I won't go through everything else. I'll simply say that these are all posted on the website. This has been going on for a number of years, at least since around 2005. If you're interested, please contact me, and that's the end of the talk.
Yeah, Tarek, thanks a lot for this really very, very broad and interesting presentation. Questions?
Yes.
So, well, maybe I ask the first question, as I don't see a hand up at the moment. Concerning this genetic type algorithm, as I understand, the genes are essentially individual simulations.
That's correct. So each of these are all the parameter settings of the entire robot system. So for example, in a typical robot system, we'll probably have 1 to 200 parameters. That's the genetic DNA of this entire process.
But doesn't this lead to the situation that many of these genes are essentially dependent from each other, which is kind of different from classical genetic algorithms? There they are independent, more or less, the different
the genes are dependent upon one another, so it's strongly coupled.
Okay.
So I mean, I hate to call it or use the word even genetic algorithm. It has genetic aspects to it, but you can think of it as the DNA of the entire process is crystallized in one of these vectors, but essentially it's a vector of parameter settings. You stick the parameter settings into the digital twin, you get the response, and you ask, how well did this overall process do in achieving the manufacturing process I wanted? At that point, then they're ranked from top to bottom, meaning best possible process, worst possible process. We delete the processes that did not achieve what we want. We reward the processes, and then we repeat the process again and again.
More questions? Mark.
Yes, thank you. Thank you, Tarek, for the nice and inspiring talk. So there's a lot of data science in what you're doing already, but can you comment on how you see the future of integrating data-driven approaches, both for mechanics and other disciplines, and even model-free approaches in this context?
Sure. So yeah, you can imagine, I mean, we're literally in the backyard of Facebook, Google, all of the people that are pushing this down our throats. All our students are taking almost, they rarely even want to take mechanics courses anymore. They all want to take data science courses. So I have to force my students to take even continuing mechanics because they want to do what Facebook does, because Facebook gives people gigantic salaries and mechanics doesn't. So there's an economic driver that is pushing us towards this direction. So the way I see things evolving, at least from my computer science friends that are all embedded in that system, they've gone to a point of stagnation, just simply a neural net without any physics-based input has only gone so far. What is now really in vogue are these physically informed neural nets. Essentially, what you have is you have some type of optimization scheme, which a neural net is nothing more than a curve fit. I mean, with fancy bells and whistles, as we all know, we have the weights and we have the activation functions. But now adding these manifolds of physically induced parameter constraints, usually multilateral, but in the simplest cases, they're unilateral, much like with what we have with plasticity or any kind of classical optimization with PDEs. Where I see things going now are neural nets with physically constrained optimization embedded inside, or the flip side, optimization based upon PDEs, but with neural nets embedding into the material data. I mean, it's almost semantics which way you look at it. Are you optimizing PDEs and ODEs with some constraints using neural nets to inform you about the material data by embedding data science in it? Or do you have a giant neural net where you're simply curve fitting things and you have physics to inform where the go, no go zones are. It's a matter almost like what you're trying to balance. For example, are you 80% neural net and 20% PDE? Are you 80% PDE or 20% neural net? The way I see it is it's a sliding scale. If you really do the codes right and in a modular way, you can go from one extreme to the other, meaning completely model free, 100% neural net, completely our old classical stuff that we all love, no neural net, all PDE. And now you have a sliding scale of where you want to drive this process. Do you want 50-50, 80-20? That's where I think the systems are going. And in fact, judging from where my students go, and they all get hired by these companies in the Bay Area, they basically see this exactly in this convex combination type approach. It's not going to be purely neural net and data science, and it's not going to be purely Abacus and ANSYS and doing models with PDEs. There's something in between. And that's what I think we as a community really need to start thinking about, which is how do we blend these model-free and model-rich systems in a seamless fashion? It can't be discontinuous where we simply say we run the model, then we do the neural net. That's, you know, a pretty old-fashioned way of thinking about it. It has to be blended together.
I agree. I agree. Thank you very much. Thank you.
Sure.
There is one more question, and I would like to read it from the Q&A session from Dominic Strobe. Thanks, Tarek, for that interesting talk. You talked about applying ROM methods for the digital twin. Which methods do you use for that?
I'm sorry, the wrong methods?
ROM.
Oh, ROM. Sorry, wrong. I thought you meant wrong methods.
No, ROM.
So it's also a question now of semantics as well, whether we're thinking of proper orthogonal decomposition and we're projecting things, or we're simply saying simplified models. So the way I use reduced order models, I really mean simplified models. It's not a formal projection going from, you know, highest scale to smallest scale. So I'm sure Charbel and I argue about this all the time. He's a ROM guy and he has a formal process of projecting from one to the other. I think at this point, you know, in 2021, we've kind of gotten to the point where we call everything a reduced order model. Is a beam model a reduced order model? Yes. Is it a simplified model? Yes. Is it a formal projection? Oftentimes not. So I think I'll backtrack and say it is simplified models with a hierarchy moving towards a more complex model. And that more complex model may be, sadly, as I think Mark was indicating, it might be model free. So there's going to be no projection. I mean, the most complicated model may be I simply saturate everything with sensors that I'm getting from the field, and I'm building the model based entirely on complete sensor data. If you look at the traffic people, which is what is going on in the Bay Area, you know, Facebook and Google and so forth, and buying habits, they have so much data that they really don't need a model. I mean, that's unfortunately not our case in mechanics, because we're never going to get that much data like people get from their cell phones 24/7. They're getting trillions of petabytes of data daily. So we have to backtrack and ask, based upon how little data we get, do we blend synthetic data and experimentally observed data together, which is unfortunately the world we're going to have to live in terms of mechanics? Or do we just simply tell the experimentalists, saturate everything with more and more sensors and allow us to get further and further down the model-free case? Reduced order models have a key role here, but unfortunately they have to be really, blended with, the neural net world. I mean, you have to tune those models, and I don't think any model is untunable in terms of being, completely phenomenological parameters free. It just depends upon where you draw the line and decide these are the parameters, and I think they're better than the reduced order parameters. That's a bunch of, I think, semantics at this point. With machine learning, you can train almost any model to match certain states. Depends upon how much data you get.